Hi everyone, it's Michael. So I have a fabulous problem for you all today. This problem, it was posted by Nair Sharar on the Art of Problem Solving forum. So he's a subscriber to my channel and he's from Bangladesh. And this problem was originally from a training camp in Bangladesh in 2015. So if you'd like to try to solve it, feel free to pause the video. Alright, so I'm going to go over the solution. So we have a cyclic quadrilateral ABCD. And the diagonals AC and BD meet at P. The circumcircles of triangle CPD and triangle ABP meet at point Q. And then we want to show that angle OQP is 90 degrees. All right, so the initial configuration looks fairly simple, but the problem is deceptively tricky. So first I'm going to note that whenever I see a cyclic quadrilateral, and I have the intersection of the diagonals, it suggests that maybe we could use Bricard's polar theorem. So for those of you that aren't familiar with that, if you watch video 76 on my channel, the last theorem of it, I described Ricard's polar theorem. So in order to apply Ricard's polar theorem, not only do we need the intersection of the two diagonals, which we have is P, but we also need to extend the two sides to meet. So I'm going to do that right here. So if I extend A, B, and CD, and I let them meet at point E, and then I also extend AD and BC, and I let them meet at point F, then Bricard's polar theorem says that EQ is the polar of F, or actually I should say EP is the polar of F. So that means OF is perpendicular to EP. So maybe we could use that to solve this problem, because another thing that suggests that we might want to use Bricard's polar theorem is that we're trying to show angle OQP is 90 degrees. So if we could show somehow that QP is the polar of F, and maybe also that OQ and F are collinear, then that would solve the problem. And it just so happens that that is the case, and that's exactly what I'm going to try to show with this proof. All right. Okay. So how do we get started? So we have three circles in the problem. And whenever you have three circles, it's often worth attempting to use the radical axis theorem. So that's what I'm going to do here. So what are the pairwise radical axes of these three circles? Well, AB is one of them, because it passes through the intersection points of two of the circles. And CD is another one. And then the third is PQ. So by the radical axis theorem, AB, PQ, and CD all have to concur at a point. But that point has to be point E, because we already know that AB and CD concur at point E. So I'm going to write this out. So by the radical axis theorem on these three circles, so the one through ABP, the one through CD and P, and the one through ABC and D, these three lines, A, B, C, D, and QP have to concur. And not only that, they have to concur at point E, which means that PQ has to pass through E. Okay, so QP and E are collinear. So I'm going to draw that segment in. All right, so we're getting close to solving the problem already, because line EP is the polar of F by Bricard's polar theorem. All right, so by Bricard's polar theorem, since EP is the polar of F with respect to the circle ABCD, that means EP has to be perpendicular to OF. So if we want to show angle OQP is 90 degrees, that's essentially equivalent to showing that OQ and F are collinear, because we know that EP is perpendicular to OF. So how do we show that OQ and F are collinear? So one way is to try to use the radical axis theorem again. So we showed that AB, CD, and QP concur at E using the radical axis theorem. Maybe we could use a very similar idea to show that BC, AD, and OQ concur at F. And it turns out, this is fairly lucky in my opinion, but it turns out that's exactly what you can do. So it turns out that you can show that AOQD is cyclic and BOQC is cyclic. And then by the radical axis theorem, that gets us exactly what we want. So I'm going to prove that AOQD is cyclic using an angle chase, and then the same argument is going to work for BOQC. All right. So I'm going to write out the angle chase here, but I'm going to compute angle AQD, and I'm going to show it's the same as angle AOD. All right. So we have angle AQD. It's equal to 360 minus AQP minus DQP. That's because there's 360 degrees in a full rotation. So AQP, DQP, and AQD have to add up to 360. Okay, so we have 360 minus angle AQP minus angle DQP. And we can break up this 360 into a 180 plus 180. So that's what I've done here. I've said it's 180 minus AQP plus 180 minus DQP. And the reason that I'm doing that is I want to take advantage of the fact that ABPQ is cyclic and CPQD is cyclic. So 180 minus AQP, that's angle ABP, okay? And similarly, 180 minus DQP, that's angle PCD, or equally angle DCP. And that's because the opposite angles of a cyclic quadrilateral add up to 180, okay? So what's angle ABP plus angle DCP? Well, those two angles, if you look at quadrilateral ABCD, those two angles both intercept the arc AD. So angle ABP, that's the same as angle ABD, which is half of the intercepted arc. And similarly, angle DCP has to be half of the intercepted arc, which is AD. So if each of them are half of this intercepted arc, then if they're equal to each other, and if you add them, they have to equal the entire intercepted arc, which is angle AOD, because that's the central angle intercepting that arc. Okay, so this is what I mentioned. So angle ABP is ABD, and angle DCP is ACD, and they're both half the intercepted arc, so together they're the entire intercepted arc, which is angle AOD. So if angle AQD is equal to angle AOD, then that means AOQD is a cyclic quadrilateral, because those two angles intercept the same segment, and so AOQD has to be cyclic. And then by the exact same argument, we can show that BOQC is cyclic. So I'm not going to write out the same argument again, but using this exact same proof, we also have that BOQC is cyclic. So we have a lot of circles here now, but now we can apply the radical axis theorem exactly like we wanted. So if we have BOQC, AOQD, and the circumcircle of ABCD, well, the three radical axes of those are AD, BC, and OQ, and they have to be concurrent, and in fact, they have to concur at point F. So we're getting kind of lucky here, but from this fact, it's clear that OQ and F have to concur. I'm sorry, OQ and F have to be collinear. And so from there, we've essentially solved the problem. Because if OQ and F are collinear, well, we set up here that EP is perpendicular to OF. So that's the same as saying EQ is perpendicular to OF. And that means that angle OQP has to be 90 degrees, which solves the problem. So this was a very cool application of Bricard's polar theorem. I kind of like how in the initial configuration you didn't have these sides extended, but by adding those extra lines to the diagram, it makes the problem much more clear. And there are ways to solve this without Bricard's polar theorem. In fact, in the link that I give in the description of my video, I'm going to show one of them. But just this idea of Ricard's polar theorem just greatly simplifies the problem. So if you like this video, give it a thumbs up. And if you'd like to see more like this, feel free to subscribe to my channel. Thanks, everyone.